Thank you, Sylvia. So thank you very much for the organizers for this invitation, this opportunity to thank the birthday. It's really, I'm thankful for all that you've done for me all these years, and it's really nice to have you around. So I apologize for being a little bit zombie today because the fire alarm went off at 4 o'clock in the morning at the hotel, and I'm on the 22nd floor of the hotel. So I had to go 20 floors down and wait in the street until the building was clear, and thankfully I could go up by the elevator, using the elevators. Otherwise, I don't think I would be here now. Okay, so today I'm going to speak about this generalization of the Hirzebruch problem, which is joint work with Sylvia Sabachini and Nicholas Lindsay, which is there, over there. And so Hirzebruch, there's the famous problem 27 that aims at determining all the complex analytic compactifications of Cn with second Betti number equal to 1. Okay, so what do we mean by a compactification of Cn? It's just a compact complex manifold with a closed subvariety A such that, oops, not this that I wanted, X minus A is just biholomorphic to Cn. If X is a smooth projective variety, we say that the compactification is smooth, and as an example, we have Cpn, where A is Cpn minus 1. So whenever we have a projective compactification of Cn with B2 equal to 1, we automatically have that it has to be Fano. In this case, the canonical divisor is a multiple of A, the hypersurface that we have to take away to get Cpn. And this multiple, it's minus R, where R is the Fano index of X, which can go from 0 to n plus 1. 1 to n plus 1. So what do we know about these compactifications? When n is equal to 1, we only have Cp1 and A is just a point. When n is equal to 2, we have Cp2 and A is just Cp1. Nothing much interesting here. But when n is equal to 3, the classification is complete and the work is due to Prokhorov, Pitternell, Schneider, Furushima, Mukai, Umemura. And we have all these possibilities. Cp3, the smooth quadric, which is the Grassmannian-oriented two planes in R5, the smooth quadric in P4, a Del Peso quintic three-folds V5 in Cp5, and a family of three-folds V22 in Cp13 of index 1. So those of you familiar with Su's work on the classification of Hamiltonian circle actions with 6 fixed points, recognize this example. So these are the only possible Hamiltonian, the only possible manifolds when you have, or at least, so when you have a Hamiltonian action with 6 fixed points, the isotropy data is going to match one of these examples. So this has already come up in symplectic geometry, Hamiltonian geometry. So when n is equal to 4, the classification is not complete. It's complete for Fano index 3, and we only have the Del Peso W5 with 4 possible choices for A, which are all singular. We don't have an A. So yeah, so the Fano index, let me go back. So the canonical divisor is a multiple of this class of A, and it's just this. Okay, let me go back. So there are other known examples. So the classification is not complete only for index 3, but there are other examples like the Fano Mukai for folds. And I forgot, I thought I had updated the last version of the slides, but apparently not. So we also have the Grassmannian of 2 planes in C4. So besides this, we have the Grassmannian of 2 planes in C4. We'll go back to these examples and describe them in a while. Okay, so all of the non-projective compactifications of Cn with B2 equal to 1 admit a C-star action, with isolated fixed points. In fact, if n is equal to 4, they all admit an algebraic, the action of an algebraic 2 torus. So there's really an action of a 2 torus. with isolated fixed points. And the restricted action of this of the compact torus of this algebraic torus on the smooth variety is Hamiltonian with respect to some invariant Kähler form. So we can always choose an invariant Kähler form for which this action of the compact torus is Hamiltonian. So this is what motivated us to study Hamiltonian torus actions on compact positive monotone symplectic manifolds. And why compact positive monotone symplectic manifolds? Because if they are Fano, they are automatically positive monotone. So positive monotone is the equivalent of Fano, or more or less, in the symplectic world, where we have C1 is a positive multiple of the class of the symplectic form. So our setting is going to be then to study Hamiltonian actions of T2, on a compact symplectic manifold of dimension 8. We'll concentrate in the n equal to 4, so dimension 8, and we'll consider the second Betti number equal to 1 and the fourth Betti number before equal to 2. I'll tell you why in a moment. And with isolated fixed points. So we want to study what are the possible T2 actions and what are the possible equivariant cohomology rings, and find out if they agree or not with those of smooth complexifications of C4. Okay? So why do we choose before equal to 2? So we know, wow, what did I do? I hope I don't do this at the last slide. Okay, so we know, so we started the proof with Sylvia, and then Dongkun, no, sorry. Dongkun Yang, no, but it's not working. I guess I have to press hard, I don't know. I told you, it's the zombie. Yeah. Okay, so now I'll press hard. So if we have 5 fixed points, so B2 equal to 1 and B4 equal to 1 with an Hamiltonian action will give you that we have 5 fixed points. And we showed that under some conditions, the isotropy data, so the data at the fixed points have to match those of the standard action on CP4. And then Yang and Tolman, they showed that this condition was always satisfied, so they completed the classification. So B2 equal to 1 and B4 equal to 1 is not that interesting because we already know it's CP4. Or it has the isotropy of CP4. We know, exactly. So the next step would be, the natural step would then be what with B4 equal to 2. Okay, so that's why we concentrated on Hamiltonian. Let's start with, actually you're going to use T2 actions, but let's start with S1 actions with isolated fixed points. And so if we have a B2 equal to 1 and B4 equal to 2, we already know that we have 6 fixed points, and so the Euler characteristic of the manifold is 6. Why do we have that? Because since we have isolated fixed points, the Hamiltonian function is a Morse function, and the Betti numbers agree with the number of critical points of index I. So Bi is equal to the number of critical points of index I of the Hamiltonian function. And so since these indexes are all even, the odd Betti numbers are 0, and the Euler characteristic is just equal to this by Poincare duality, and we have that it is equal to 6. Okay, so as usual, we can, since we have a symplectic manifold, we have, it is almost complex, and so we can talk about Chern classes, Chern numbers, etc. So if we assume that we have a circle action, what restrictions do we have on these Chern numbers? Do we have any restrictions from the fact that we have a circle action on a manifold? And so for this, I'll just want to, so everybody in this room knows this, I'm sure. So whenever we have a circle action, we have a neighborhood of a fixed point is modeled by Cn, and the circle acts on this direction with a certain speed, and it's certain either counterclockwise or clockwise. That's going to define the sign of the weights, and these are then the integer would give you the speed and the direction in which each direction in Cn is being rotated. So these are what we are going to call weights of the circle action in this talk. Okay, so we have the assumption that we have isolated fixed points, and we'll call nj the number of fixed points with j negative weights. Since the action is Hamiltonian, we already know that nj is equal to the Betti number 2j. So the Betti number 2j is equal to the number of fixed points with j negative weights, because this is going to be equal to the number of fixed points with critical points with index 2j. Okay, so what are the possible Chern numbers? Do we have any restrictions? So the first one is very easy. Cn of m is just equal to the Euler characteristic, and so as we said before, is equal to the number of fixed points. We just add all these nj's. Are there any restrictions on other Chern numbers? And so an old result with Sylvia from 2012 already, that under the previous hypothesis, we have that C1, Cn minus 1 is also only depends on these nj's. In particular, we have this condition where I already have translated here. I put the other characteristic. We can write it like this. So it only depends on the nj's. It only depends on the fixed points and the number of critical points with a certain number of negative weights. Okay. So in our case, since we have n equal to 4, C1 Cn minus 1 is C1 C3. If we substitute everything in the formula, we get that this is minus 14, the Euler characteristic is 6. And since we are assuming B2 equal to 1 and B4 equal to 2, we have that this Chern number must be equal to 48. So whenever we have an 8-dimensional manifold with an Hamiltonian S1 action with isolated fixed points with B2 equal to 1 and B4 equal to 2, we already know that C1 C3 must be equal to 48 and C4 must be equal to 6. More information? Actually, yes. So in this work with Nicholas and Sylvia, we prove that under the above conditions, if C1 is not a primitive element in H2, then there are only finitely many possibilities for all Chern numbers, okay? And actually, so we are going to divide these manifolds. So we are going to consider the index of the manifold as the largest integer for which C1 is a multiple of another class in H2. So this was going to be the index. And since we have an Hamiltonian action with isolated fixed points, Sylvia, in her paper from the Hilbert polynomial, showed that the index must be between 1 and n plus 1. And so since we are dealing with n equal to 4, we get that the index must be from 1 to 5. But since C1 is not primitive, we are assuming that C1 is not primitive, right? We're assuming here that C1 is not a primitive element in H2. We know that the index cannot be 1. And since the index divides C1, it must also divide C1, this Chern number, so it must be a divisor of 48. So in our situation, the index can only be 2, 3, or 4. Okay, but actually we have all these a priori possibilities. We were able to prove that these are the only possibilities for the Chern numbers. So the first case is for index 4. These two lines are for index 2, and we have all these possibilities that we cannot rule out a priori for index 3. I'll show you how to prove some of these things. So also in Sylvia's paper on the Hilbert polynomial, she computes, so she shows that when the index is 4, then we really have these values on the first line. So sorry, here on the first line. So these are already in Sylvia's paper. Then she also has for k0 equal to 3, for index 3, we have these relations that the Chern numbers must satisfy. If for index 2, we have these equations. So what we already have is then we know that C1, C3 must be equal to 48, C4 must be equal to 6. So these two last columns are already proved. And Sylvia showed that C2 squared must be equal to 98 when the index is 4 and 2. So we already have this column here. And so we are left, and we also have the first line also in Sylvia's paper. So we are left with everything that is in blank. I'll show you how to prove this in blue. The others are similar, so I'll just spare you. I'll just show you how to prove, for instance, these two possibilities for the Chern numbers. Okay. So we have this equation from Sylvia's paper that relates C1 squared C2 with C1 4. So we choose an orthonormal basis of H4 with two elements. Recall that B4 is equal to 2. We choose the orthonormal basis with respect to the symmetric bilinear form determined by the cup product on H4. And so we write C2, which is a 4 form, as a linear combination of these elements of the base. And so C2 squared, which we know is 98, must be equal to A1 squared plus A2 squared. And the only way of writing 98 as a sum of two squares is when A1 and A2 are equal. Yes, yes. Mm-hmm. And so we have that sorry?
No, I'm just wondering if is it obvious that there is an orthonormal basis?
Yes. Sorry. Yes, we have here the cup product in H4, and this is a bilinear form, and there's a finite number of classes of these bilinear forms, and it turns out that this has to be in the Euclidean class, and we can pick the class of the Euclidean class.
So it's requires something. So it's not obvious.
No, it's not. Yeah, once you know it, yeah, exactly.
Okay, thanks.
Yeah, it has to be in the class of the Euclidean bilinear. Okay, of the Euclidean inner product. So we have this. So the only possibilities is for A1 and A2 to be equal to plus or minus 7. And so C1 to the fourth, if we, C1 squared, we can, okay, sorry. So we already have this. And now we can also write C1. As we know, we are assuming index 2. So C1 is 2 times tau, where tau is a primitive class in H2. And so C1 squared is 4 tau squared. We can also write it, since it's in H4, as a linear combination of V1 and V2. And so C1 to the 4 can be written in this way. Substituting in our equation, we get that the only possibilities for A1, for D1 and D2 are these. So these will give you, if you plug this, so we had that C2 was equal to A1, V1, A2, V2, with A1 and A2 equal to plus or minus 7. And now we know all the possibilities for D1 and D2, so we get all the Chern numbers for this index 2. Okay, so now let's go to the known examples of projective compactifications of C4. Sorry, there's another mistake in the card. So here should be, oops, it should be C4. So the projective compactifications of C4. So the first one comes, so we start with the Grassmannian of two planes in C5, which can be embedded by the Plucker embedding in CP9. And we take the intersection with the codimension to projective subspace of CP9. So this can be embedded in CP9. We take an intersection with the codimension to space, and we get what is known as a Del Piezo fourfold of degree 5. Sorry. So further, what we do, so we can take an hyperplane section of this W, and if we remove this hyperplane section, we get a set that is biolomorphic to C4. So W is a smooth compactification of C4. So it's the intersection of the Grassmannian of two planes in C5 with a codimension to projective subspace in CP9. So Prokhorov and Zeidenberg prove that is there any problem online? So they prove that if we blow up W along so there's a special CP2 inside R, this hyperplane section of W. And if we blow up W along this special CP2, we get the same an isomorphic manifold to the blow up of CP4 along a twisted cubic curve here. Okay, so from here we are going to be able to say something about some special T2 action. So Prokhorov and Zeidenberg also show that the automorphism group of W coincides with can be identified with the automorphism group of CP4 that leaves this twisted curve invariant, and also that this hyperplane section is invariant under the automorphism group. And they showed also that there's a 2 torus act inside the automorphism group that acts on C4, and they compute the action on C4. So on C4, we have an isolated fixed point, and we have these weights for the T2 action on C4. This action is not effective. There's a diagonal Z3 that fixes everything. Okay, so from here, so that's what they did. So they said they proved that they had a 2 torus in the automorphism group, and they showed that they had these weights on the fixed point that is on the C4 part of the compactification. So using the fact that these blow-ups coincide, we are able to obtain the weights at the other, so we are able to prove that there are other 5 fixed points, so in total we have 6 fixed points, and we are able to show that these are the weights. How do we do this? So if we take the projective span of this cube, exactly the twisted curve, we get some CP3 inside CP4, and we have this twisted curve which is contained in this H. So what we do, we are going to blow up along gamma, and when we blow up along gamma, each of these, so gamma intersects H at 2 fixed points. So when we blow up along gamma, each of these 2 fixed points is going to originate the exceptional divisor above these 2 fixed points is going to be 2 projective planes. So each of these fixed points is going to give you 3 fixed points on the blow up along gamma. Okay, so here in yellow is H, here and here, and here is the proper transform of H after the blow up. So now we know, we know the weights of 1 point in CP4. If we know a weight of 1 point in CP4, we know the weights at all the other fixed points. So we know the weights here. So we are able to put the weights on all on the blow up of CP4. We are able to determine the weights here on this side of the picture. So we know the weights on the blow up of W along sigma. And the exceptional divisor of sigmas when we blow up along sigma is going to coincide with the proper transform of H. So now to get the weights at W, we just have to blow down along sigma. So what we do to blow down, now sigma is 4-dimensional. So when you blow up, you get that the fixed point is going to originate a sphere in the blow up in the exceptional divisor. But when you go back, so what you have, now we have to go back from the right to the left. So in order to determine the weights after we blow down, so what we have to do, we just have, and to find out what are the points that are going to be identified, we just have to look at points with what happens here. So we have that the weights at this fixed point and at this fixed point in the tangent that are tangent to the exceptional divisor, they must agree. And the ones along this sphere on the exceptional divisor are symmetric. So we just have to look at these 3 pairs of points and look what are the ones that have a pair of common weights and a symmetric weights. And so we find out that B can be identified. So when we blow down, this point B is identified with this, the blue one is identified with that, and the red one is going to be identified with that. So we end up with 6 fixed points on W when we blow down here on this space. And so the moment map image is going to be given by this, and this red line is just the image of an isotropy CP2. So this is not a GKM space. And as I told you before, so T2 is not effective, does not act effectively. There's a diagonal Z3 that fixes everything. So we quotient by Z3 to get an effective action on W. So W is known to be a Fano variety with index 3. And we know that it exists a Kähler form for which this T2 action is Hamiltonian, and we can rescale it so that C1 agrees with the class of omega. So second example, second known example. So we start with a generalized flag manifold. We'll take the complexification of the exceptional Lie group, which has complex dimension 14 and can be identified with the automorphisms of the Octonian algorithm over C. And we take the parabolic subgroup, which corresponding to a long root with dimension 9. So if we take this quotient, we get a space, this generalized flag manifold in CP13. This space is GKM and it has a T2 action with this graph. This is known. And so now we are going to consider, again, an hyperplane section of this omega. So we take an hyperplane section, an intersection with some CP12 inside this CP13. And we obtain the Fano-Mukai fourfold with index 2. So the moduli space of these manifolds is one dimension. This was proved by also Prokhorov and contains two special elements with automorphism group C times C star, so the abelian group and the multiplicative group C star, and another element which has automorphism group GL2C. But any other general element in this one-dimensional family contains the multiplicative, so C star times C star in the automorphism group, and so it contains the compact 2 torus in the automorphism group, which is the restriction of this GKM action that we had on omega. So on omega we had the GKM action of T2, and we are just going to restrict it to V. So this was the GKM graph for the T2 action on V, on omega. To obtain the GKM graph on V, we just have to find out which are the edges that are going to be suppressed when we restrict to omega, when we restrict to V, sorry. So we know that the index is 3, so C1 is 3 times the primitive element in H2, and this primitive element must be Poincare dual to the class of V in H8. So we want to find out what are the invariant spheres that only intersect V in two isolated, in the two fixed points. And so we know that this intersection number is 2. And so since tau is 1/3 of the class of omega, we see that the class of the area of these spheres that are going to be suppressed has to be 6. So these correspond to the blue ones. So we know that if we start with this GKM graph and we erase the blue ones, we get the GKM graph for the T2 action on V. Okay? Okay, so we have our 2 examples. The third one is known, the Grassmannians of complex 2 planes is C4. This was the one that I had forgotten, which is known to be the degenerate conjoint orbit of CU4, and it has a T3 action with 6 fixed points. So this actually has a T3 action with 6 fixed points, and the moment polytope is the octahedron here. Okay, so we will see that all the possibilities for Hamiltonian T2 actions, we have the same fixed point data and the same equivalent cohomology as one of these 3 examples. So these are the only possibilities, and they are all compactifications of C4. Okay, so for that, let's go back to circle actions, and we are going to associate to circle action a family of multigraphs. So for each vertex, so the vertices correspond to fixed points. The edges we're going to, so at each fixed point we'll have a certain set of weights, and we are going to connect fixed points, pairing them with whenever they have weights, opposite weights. So this fixed point here, sorry, I'm having trouble, has for instance, a weight 1, and this will have weight -1. So we can pair them and we can join them with an edge. And we are going to label this edge by the absolute value of the weight. Okay? So for each possible pairing of these weights, we get a multigraph. So if we consider the multi-set of all weights of all the fixed points, it can be decomposed in the multi-set of the positive weights, the negative weights, and Hattori proved in 84 that the multi-set of positive weights must be symmetric to the multi-set of negative weights. This is well known. So for instance, in this example, this would be the multiset of positive weights and the one of negative weights. So for instance, we have here just two examples of possible pairings of weights in W plus and W minus. We could pair them like this or pair them like this, so we get two possible multigraphs, for instance, with this. So Young and Tolman showed that these multigraphs cannot have self-loops because in principle, so if, for instance, a fixed point has weight 1 and minus 1, it could be paired with itself. So Su and Young rule this out, so we cannot have self-loops. So given a multigraph, for each edge, we are going to define this integer, which is going to be just the sum of the weights at the tail of the edge minus the sum of the weights at the head of the edge divided by the absolute value of the weights with which we labeled the edge. Okay. In 2014, we showed with Sylvia that the sum of all these, we call these magnitudes, the sum of these m's must be equal to the Chern number C1, Cn minus 1. So we just write this, use a localization formula to compute C1, Cn minus 1, and we can write it in terms of these sums of weights at the fixed points, and we get that it's equal to the sum of the magnitudes. So then what we do, we define a function for each graph, we define a function on the set of vertices and edges, which is going to give you 1 if the tail of the edge coincides with P. So delta of PE is 1 if the tail of the edge is equal to P. It's minus 1 if the head of the edge is equal to P, and 0 otherwise. So for instance, here delta would be 1 because the tail is P. Here would be minus 1, the head is P, and here it would be 0 because we have none of these. Okay, so now what happens if we fix an edge, a particular edge on the set of edges, and we sum for all the edges, we sum this. So what does this do? So this will give you plus or minus 1 or 0 according to if E has starts. So it's going to be 1 if E starts at the same point as this particular edge that we picked. It's going to be minus 1 if it ends at the point, and it's going to be 0 if none of this happens. And we are multiplying these by the absolute value of the weights. So this will give you the right signs, so that when you multiply by the absolute value of the weights, will give you the sum of the weights at the tail of this edge that we picked. And this will give you the sum of the weights at the head of the edge that we picked. Sorry. So whenever we had this, when we get that this left-hand side is going to be just this difference between the sums of the weights. This part here, so this is the absolute value of the weight of the edge that we picked, that is going to be multiplied by this magnitude of the edge, which is equal to this, so this k cancels, and we have again the sum of the weights at the tail minus the sum of the weights at the head. So when you do this difference, you get 0. So for each edge that you pick, you get an equation, you get a relation, you get that this must be 0. So how many edges do we have? So we are considering B2 equal to 1 and B4 equal to 2. So we have two index points, two fixed points with index 2, with index 4. One in so we get 4 edges from here and one additional edge. Okay, and then one edge here. We have no edges for coming up from the maximum, so we have 12 edges. So we lost the zoom. It's coming back. I think so. Yes. Okay, so we have 12 edges. We get 12 equations. For each edge we pick, we get 12 equations. So for each edge that we have. We get one equation, we obtain 12 equations, and we can write it in this matrix form. So for each graph, so each multigraph, we can construct a matrix A, which is going to be with these coefficients that we have here. That is going to be multiplied by this weight vector, the vector of absolute values of the weights. And here we can write this as a diagonal matrix where we put here the magnitudes of each on each edge of the multigraph. Okay, and we know that we have this linear system of equations that must be zero. So what we get from here, we get that this vector of the absolute value of the weights has to be in the kernel of this matrix. So this matrix must have non-trivial kernel. Okay, so this is what I just said. We have that this vector has to be in the kernel of this matrix, and it has to be, these are the absolute values of the weights. So this kernel not only has to be non-trivial, it has to contain vectors with all positive entries, so that this is possible. Okay, so with this we can obtain an algorithm that, given your prescriptions, a certain number of fixed points with a certain number of indices, will give you all the possible weights that you could have. Okay, let's see how to do this. So we consider all multigraphs that can come from the pairings of the fixed points. We don't know a priori the weights, so we just have a bunch of fixed points, and we are going to see all the possible multigraphs, all the possible pairings between fixed points. So we have a collection of multigraphs. And so for each multigraph, we get a matrix, this matrix A, and we'll obtain a family of matrices. And we'll now look for the possible functions, possible magnitudes, for which, when we substitute these magnitudes on the diagonal matrix and we subtract from A, we get a matrix with kernel, non-trivial kernel, such that the intersection that contains vectors with positive entries. When they exist, the weight vectors are in the kernel then of these matrices. So, since we know that the sum of the magnitudes must be equal to C1, C3, it's always equal to C1, Cn minus 1, and C1, C3 in this case is equal to 48, we know that these magnitudes have to form a partition of 48. If we assume that this function is always positive, so let's consider first that it's always positive, we are going to look for the possible partitions of 48 in 12 positive integers, and so we get a finite number of possibilities for M, and the algorithm finishes. Okay? So this is always the case when we have the other characteristic 6, and the S1 action extends to a T2 action. So we could always find a positive multigraph, meaning that we can always take a magnitude function that is positive. So our algorithm, what does it do? So it's going to look for the possible partitions of 48 into 12 positive numbers, substitute these on all these matrices, and look for those that have non-trivial kernel with some vectors with positive entries. So this is what the algorithm does, and we know that it finishes. So we can improve it slightly, because we know that since K0 divides C1, we know that all the magnitudes, since the sum of the magnitudes is C1, Cn minus 1, and also because the magnitudes are actually the weights at the head minus the weights at the tail, or the other way around, divided by K. So this is actually C1, the equivariant C1 evaluated at each of these points. It's the difference between that. And so K0 must divide these magnitudes. So we can improve. What are we going to do? We're going to divide our problem into one index at a time, and we are going to look for partitions that for all the entries of the partition, all of the elements of the partition must be multiples of this index. So when index is 2, we are going to look for even partitions of 48. Index is 3, multiples of 3, etc. Okay, so we run the algorithm, and we obtain tentative two-dimensional families of multi-sets of weights, the ones that give you non-trivial solutions, non-trivial kernels. And then we check several conditions imposed by the localization formula. For instance, we know that the integral of the equivariant C1 forms, the powers of the equivariant C1 form must be equal to 0 for powers smaller than 4, right? And so we get some conditions. So running the algorithm, we get tentative families of multisets, and then we're going to check which of these families satisfy these conditions given by the localization formula. And so we get that when index is 1, if we assume that K0 is 1, there's no solutions, okay? So there's no circle actions with 6 fixed points with B2 equal to 1 with index 1, okay? That is ruled out. So it's the best way, so we have nothing else to do. With K0 equal to 2, we just have one possible multigraph. So this is the only multigraph that will give you a matrix with non-trivial kernel. And we have just two possible families of weights, okay? And these families of weights will give you the weights of the two families of 42 actions here. They are actually the same, they're just with different bases. And these are actually, sorry, I told you that I uploaded the wrong, the wrong file, sorry. So they have the same T2 action, the same data as the T2 action on the Fano-Mukai fourfold of example 2 that I showed you before. Okay, and the Chern numbers are the Chern numbers that we had on this, on the second line here. So with K0 equal to 2, we had these two possibilities a priori, but the only possibility that shows up is this one on this line. So these are the possible Chern numbers.
So line 1 and line 3 are not.
No, line 1 was for K0 equal to 4. So, but the one that is not possible is the third line. Okay, so for K0 equal to 3, we ran the algorithm, we obtain our families of multisets, the localization conditions from the localization formula, and but that is not enough to rule out all the possibilities that we can. We are going to also check that we know that we had proved that the Chern numbers had to be on this table when index was 3. So we are going to impose that the Chern numbers must be these. And we get that there are only 6 possible families of weights. Okay, this is what the algorithm gives us, and just 2 possible multigraphs. Okay, and these are the same data as the T2 action on the Del Pezzo W, just picking different bases and the different points, fixed points for the minimum of your circle action, because these multigraphs correspond to circle actions inside your T2, picking different orientations on this, picking your different fixed point to be the minimum of this circle action, you get these 2 possibilities. So
They're the same.
they're actually the same. If you think about T2, it's the same data as in the Del Pezzo W. And the Chern numbers now are only on this line. So the other lines are not possible, okay? So.
And you know that that example doesn't occur in the answer.
That doesn't
There
occur.
is such an animal.
Yeah, it's, I've just described it. It was this Del Pezzo fourfold W. Okay.
You
Okay.
have examples of
For all of these,
possibilities.
yeah,
I mean, there may be others, but everything that occurs
is
actually real.
exactly. Okay. And for K0 equal to 4, for index 4, there's only one possible multigraph and one family of weights. And in this case, the family is 3-dimensional, which corresponds to the C3 action on the Grassmannian that we had before. And so we have the same again. So the 3 examples that I told you about are exactly the ones that show up running the algorithm. So that's nice, so that we don't mess up. And for here, we get the only line possible for K0 equal to 4, for index 4 was the first one, which, thank God, it was, okay. Okay, yes. And so, what is our conclusion? When we have an 8-dimensional compact symplectic manifold with a T2 action with 6 isolated fixed points, we know that the index must be 2, 3, or 4. And the isotropy data, and we are also able to compute the cohomology ring and the equivariant Chern classes using the canonical classes of Sue and Rebecca. And we are able to compute everything. And they agree all with the known examples, the Fano-Mukai fourfold V with the T2 action when index is 2, the Del Pezzo fourfold W with the T2 action when K0 is 3, and the Grassmannian when K0 is 4. So this is our result. There are some additional results that we can obtain using our algorithm with 8-dimensional manifolds if we assume that we have an S1 action with isolated fixed points and that the index is not 1. So if you assume that the index is not 1, and we are going to assume that the S1 action can be described by a multigraph that admits a positive magnitude, meaning that we can find a function, this function on the edges, that is positive, just for the algorithm to finish. So if we assume that this exists, we are able to prove that there are only finite possibilities for the Betti numbers. So in particular, we have this, okay? So how do we show this? So unimodularity of the Betti numbers is already proved by Yuni and Shu. And so what we have that the sum of the magnitudes must be equal to C1, Cn minus 1, or in this case, C3. Okay, and this can be written in terms of Betti numbers. So we can be written in terms of Betti numbers. But we know that each of these magnitudes is a multiple of K0, okay? So we know that we have 12 edges. So we know if we subtract, so we know that this must be greater or equal than 12 times K0. And if we subtract this, we get that it must be then greater or equal, must be non-negative. So from this, you get conditions on the Betti numbers, and we get this.
And the fourth bullet is sort of like a fan type.
What do you mean?
Yes. Like type. I'm not saying that. So for instance, it falls into a GKM space.
Yes, that's.
Right? And if you wanted to get to the plus omega, then you want to
Yeah.
sort of in that direction.
Yeah, like it's what I was saying. So if we assume that we have a GKM action, then we no longer have to assume that we have a positive function, this magnitude, because it already comes for free. And so the algorithm finishes. And so if we assume that the action is GKM, then we have this. And we remember that when B2 and B4 was equal to 1, 2, the case that we previously talked about, the only example possible was not GKM. So this was ruled out. So when we assume that it's GKM, actually we have fewer possibilities, and we have this. And we even ran the algorithm when B2 is equal to 1, and we left before go from 1 to 6. So with B2 greater than 1, then the algorithm gets very slow. So we didn't run it. So, but with so let's see. So the algorithm, what did you tell us? What did it tell us? Here we already know that when B2 and B4 are equal to 1, we have the same data as CP4. This was known. When B2 is equal to 1 and B4 is equal to 2, and the index is 4, I already told you about. This is the Grassmannian of 2 planes in C4. When K0 is equal to 3 and GKM, this is the only possibility. And when we ran the algorithm, with B2 equal to 2 and B4 equal to 3, and we got that we have the same data as the action of the toric action of T4 on CP2 cross CP2. So we get this example. And here, when the index is 2, and we take B2 equal to 1, and we let B4 go from 1 to 6, we see that the only case that gives you solutions is when B4 is equal to 2. And then we get the same data as in V. So we didn't run it with B2 greater than 1. Okay, thanks.